Today's episode dives into three exciting frontiers of generative AI: video, images, and audio. We'll look at a new video framework that plans semantics in latent space for more faithful editing, a spectral diffusion method that speeds up image and video generation by growing resolution only when needed, and a powerful audio model that can create and edit stereo sound for minutes at a time. Together, these papers show how AI is becoming faster, smarter, and more creative across every medium. Let's explore the first paper, Bernini Latent Semantic Planning for Video Diffusion. Bernini proposes a two-module video generation and editing framework that uses an MLLM planner to predict target semantics in the model's own ViT embedding space, then a WAN2, two-derived DIT renderer to synthesize pixels in VAE latent space with cross-attention to those semantic embeddings, text features, and source VAE features for preservation. Its main novelty is treating ViT embeddings as the semantic interface, which lets the planner and renderer be trained mostly separately and then lightly co-trained, reducing interference while retaining pre-trained capabilities. The paper adds segment-aware 3D rotary positional embedding, or SA 3D rope, which injects segment index phase modulation so the renderer can distinguish multiple reference images or videos that share the same spatiotemporal coordinates, and it adds chain-of-thought reasoning in latent space to improve instruction following. Training uses a large multitask corpus, including 20 million video pairs, nearly 30 million image pairs, and 1 million reasoning augmented samples. On Bernini Bench, Bernini raises V2V overall score from 3.3 for WAN2, 7 to 3.49, and achieves 3.5 on RV2V overall score, while on OpenVE it reaches 4.04 overall versus 3.18 for Vino. For subject to video, it achieves a FaceSim score of 78.2, more than 20 points above Kling03's 57.2. Let's explore the second paper, Spectral Progressive Diffusion for Efficient Image and Video Generation. Spectral Progressive Diffusion introduces a training-free and fine-tunable acceleration framework for pre-trained diffusion and flow matching generators by exploiting spectral autoregression. Low-frequency structure emerges earlier than high-frequency detail, so the method keeps early denoising in a smaller token grid and expands resolution only when the model's power spectrum predicts that finer frequencies become signal-dominated. Its core mechanism, spectral noise expansion, uses an orthonormal transform such as DCT to carry partially denoised low-frequency coefficients into a larger grid, while injecting newly available high-frequency coefficients with correctly scaled Gaussian noise, then realigns the time step analytically. The paper derives a delta-optimal transition schedule from the measured power spectrum with fitted exponents. Beta equals 1.9155 for flux, 1 dev latents, 2.4227 for WAN, 2.1 video latents, and 2.4493 for pixel gen pixels. So the schedule depends on a single error tolerance hyperparameter rather than brittle manual heuristics. On FLUX, 1 dev at 1024 squared, the method reaches 7.09 times wall clock speedup and 7.36 times flops reduction, while preserving competitive image reward, clip IQA, NIQE, T2I, comp bench, and gen evol scores. On WAN 2.1 video generation at 720p, it delivers 2.54 times speedup. The fine-tuning recipe, implemented with LoRa rank 32, narrows the training inference gap further, and on Z-image improves the 5.0 step baseline to 7.81 times speedup at matched or better prompt alignment, while also enabling frequency-based image editing that outperforms STEdit in geometric consistency and stylization fidelity. Let's explore the third paper, Stable Audio 3. Stable Audio 3 is a family of latent diffusion models for text-to-audio generation and editing that combines a 4096 times semantic acoustic autoencoder with a diffusion transformer, enabling stereo 44.1 kHz audio generation of up to 6 minutes 20 seconds. Its main novelty is native variable length diffusion. Instead of always generating a fixed maximum length latent and wasting compute on silence, the model allocates latent length proportional to the requested duration, which makes short clips efficient and allows inference to scale from 0.44 seconds for 2-minute small models to 1.8 seconds for 6-minute large models on an H200 GPU. The autoencoder, based on SAME, preserves fidelity with multi-resolution STFT losses, adversarial training, chroma and interaural level difference regression, and contrastive latent alignment, while producing 2, 5, 6 dimensional latents at about 10.76 Hz. The diffusion transformer adds 64 learned memory embeddings, adaptive layer normalization for time step and duration, T5 gemma text cross-attention, and in-painting through local additive conditioning. Medium and large further use differential attention. Training proceeds in 3 stages: flow matching with mini-batch optimal transport coupling, a distillation warm-up from a frozen teacher, and adversarial post-training, using a relativistic discriminator plus clap-based text alignment. On the song describer dataset, large achieves FAD 0.1 at 190 seconds versus 0.128 for stable audio 2.5, while on BBC sound effects, it reaches FAD 0.358 at 5 seconds, outperforming whoosh flow at 0.58. The open weight, small, and medium checkpoints are released, with medium fitting in about 6.5 gigabytes VRAM and small running on a MacBook Pro M4. That's a wrap on today's AI paper highlights. Thanks for watching.